I'm going to talk about the merits of terrestrial analogues, which is kind of a bit of a different change of tack from the rest of the talks here this week. It's actually quite good timing, I think, because I'll probably return to some of the main points that we've come to a few times during the week as I go through this. So, yeah. So the way that robotic exploration works is we have a body of interest that we're trying to learn about. We have a spacecraft that returns some data. This data is essentially meaningless without the context provided by lab experiments, lab measurements, and modeling. And it's kind of this integrated feedback conversation that we've been talking about all week. And that's what allows us to then kind of understand, or at least begin to understand, our body of interest. One example of how that works on Europa is, as we've been talking about, we have these near-infrared spectra, and we measure candidate materials as pure phases in the lab under relevant conditions, and then use models to kind of best fit that mixtures of those to the European data to try and kind of understand surface composition. But I'm here to argue that actually natural terrestrial analogues could and should potentially provide a crucial part of this conversation. And natural analogues allow us to do two things. We can, first of all, look at a feature or a process in its natural geological or geochemical context and study it in detail here on Earth. And also, equally as important, it gives you a test bed for the development of future instrumentation or future analytical protocols for upcoming missions, especially landed missions. So whilst the lab experiments allow you to kind of control things in great detail, natural environments often behave in ways that the experiments don't anticipate. So it's this kind of crosstalk and the integration of these two approaches that we need to kind of bring to bear on this problem and to feed into the modeling. That approach has been absolutely invaluable and continues to be invaluable in Mars exploration. And I think that something similar will be needed to support Europa Clipper and JUICE, of course, and also especially a lander mission. Great, so analogues are important. But one big problem, one obvious problem, is we're sat here on a terrestrial rocky planet with a thick atmosphere, liquid water oceans at the surface. It's quite difficult to see how you could find an analog for an icy moon surface here on Earth. But we think we found a fairly compelling one. So this is Axel Heiberg Island in the Canadian high Arctic. We're up here at about 80 degrees latitude in the Nunavut province. It's a polar desert climate, a totally uninhabited island, apart from a few scientists. This is it up in the Nunavut province, up near northern Greenland. The geology of Axel Heiberg is such that it's underlain by carboniferous evaporite. So these are the remains of an ancient ocean about 300 million years old, predominantly gypsum, anhydrite, and halite in composition. And they pop up all over the island just through relative buoyancy from the overlying volcanic rocks as these dipiers, and they're exposed in at least 50 locations all over the island. They're very obvious when you start spotting them. You see them from the air. This is actually the highest concentration of exposed evaporite dipiers anywhere on Earth outside of Iran, and it's the only place in the polar latitudes where you get this. And that's crucial because on Axel Heiberg we also have about 400 to 600 meters of permafrost. And it's this juxtaposition of the permafrost and the evaporites which drive the formation of these really unique series of springs. So these things are cold. There are sub-zero C all year round. The fluids emerge from these outlets here. They're anoxic. They're highly saline, containing up to 28% of sodium chloride and high levels of sulfates as well. And they precipitate these large aprons of polyhydrated sulfates and chlorides of the type of things that have been used in linear mixing efforts for understanding European surface composition. Also, importantly, they are known to host active microbial communities, albeit very slow-growing active microbial communities. This is important, another merit of analogues, and I'll get back to that a bit later. So I was part of an expedition up to Axel Heiberg in July 2017. We sampled 3 of the 4 known cold saline springs on the island. Here they are. Here they're quite geographically separated. And I'm going to just introduce them briefly each because they're quite different from each other. So the first one you've seen a few times already on the slides. This is Lost Hammer Spring, a different view of it here. it emerges from a single outlet, which is in the middle of a dome of salt here, basically from the middle of a flat valley floor. It's seemingly at random, and you have a drainage channel coming down the side here, where the brine is being drained away from the outlet. But we think in winter that this dome that I'm stood in here, it's about 2 meters high, where the brine outlet is. Here's a side view of it. We think that gets dammed, the outlet channel gets dammed with salt in the winter. This thing fills up with brine and then overflows, precipitating this apron. Color Peak Spring down here is visually very different. It's precipitating all these dark green terraces. The brine here is a bit warmer, actually, about 4 degrees C all year round. And then Stolz Spring is just on a different scale to the other two. This thing is about a kilometer scale long deposit of salts. To get a sense of scale, here's a person stood at the boundary there between the gray salts and the whiter salts. These are sub-zero again, sub-zero C. They emerge at about -3 degrees, and we think in the winter that it becomes dammed with precipitates and flows over the top, forming these pools and terraces, and this kind of kilometer scale deposit filling this ravine. So just briefly, we can use high precision hydrogen and oxygen isotope measurements to trace the origin of the fluids that are forming these springs. And there was some previous hypotheses that they were being sourced from deep aquifers or ancient seawater hosted in the evaporites. But our data, because they sit nicely along the local meteoric waterline, this is telling us that the fluids feeding the springs are essentially meteoric. So they're local snowmelt or glacial meltwater or something like that. It's a little bit more complex than that because in a lot of cases, the springs brines themselves have quite a different composition from local contemporary snowmelt. So there's maybe some more complex process of meteoric water being cycled through the deeper evaporites for a long enough time to acquire high solute loads before being delivered to the surface. So now if we go to look at the actual composition of the deposits and the brines, you can see this is a bar chart here of quantitative XRD measured at room temperature of the 3 different springs. And you can see, without even really looking at the mineralogy, that just by visually, that these things are qualitatively different from each other. The mineral assemblages at the 3 springs are quite different. And these springs have very similar major ion chemistry. So these differences are really driven by a difference in the chloride to sulfate ratio between the 3 springs and differences in calcium content and alkalinity as well. So if we look now at the actual composition, Lost Hammer is really dominated by sulfate salts. These dark bands are mirabolite, polyhydrated sulfate. We get up to sort of 100% sulfate in some cases. And it's important to point out that whilst this has the highest sulfate content of the 3 springs, we're still looking at about 100-to-1 chloride to sulfate ratio. This is showing us that, at least on a local scale, you can get a very sulfate-rich mineralogy from basically a chloride-dominated fluid. And then we move to Stolz, which is essentially much more chloride-rich mineralogy, and Color Peak actually dominated by things like gypsum and calcite, which is what's forming those dark green terraces. The anhydrous salts we're seeing here, like the phenodites and the halites, we think, because these were measured at 20 degrees C, are basically just dehydrated, hydrated salts. And when we look at the near-infrared spectra, we can start to see, the effects of that temperature change quite clearly. So we measured these salts at 3 temperatures. We brought samples back to the lab. We measured them at 293 Kelvin, about room temperature, 253 K, about -20 C, and then at sort of ballpark European surface temperature of 100 Kelvin. So some of the thermally stable minerals like gypsum, you're not seeing much difference in the 3 temperatures other than just a sharpening of those spectral details that we all know to take place. But we move into the Stolz salts, or the Lost Hammer salts. We do see at room temperature a massive loss of these hydration features, just extensive loss of water bands. What's interesting though is that the big difference is really between the 293 and 253 Kelvin lines, and actually the difference between the 253K and the 100K, despite the much bigger temperature difference, is minimal. We're not really seeing much of the band narrowing or sharpening or band minima shifts that have been sort of characterized with pure phase salts. This is interesting when we think about Axel Heiberg in the natural environment. The temperature, it's very cold there, unsurprisingly. we spend most of the year below 0C, and actually significant portions of the year actually below this 253 Kelvin line here, which means that these kind of signatures will be stable over large portions of the year. It's only really in the summer months here, when we get above 0, that these deposits start to become dynamic and evolve with atmospheric conditions, maybe dehydrating and rehydrating with temperature. We saw some of that in the field. These are two images of the same location on the Lost Hammer deposit taken a few days apart. You can see the temperature has changed. And what we think is happening here is that you're getting a very thin crust of essentially halite. Is that 20 minutes? Oh, sorry. I've got just a couple more slides. A thin crust of essentially halite appearing on top of these darker salts here. So going back to the near-infrared spectra, here now on the right are just zoomed in on the two main hydration bands with the continuum removed. And what I want to draw your attention to is the Lost Hammer salts down here. What we're seeing is very smooth, very broad absorptions, even at 100 Kelvin. Mike was saying the other day that a lot of the times we measure these pure phase salts, we get these bumps and wiggles appearing at cryogenic temperatures, and a lot of the linear mixing efforts has been trying to basically smooth out those bumps and wiggles. Well, the Lost Hammer salts are doing this for us naturally, basically. They're very mirabolite rich, and we know mirabolite is one of these salts that forms these sort of spectral details at cryogenic temperatures, but we're not seeing them here. So this is kind of an assemblage that's smoothing itself out as a natural version of some of these linear mixes that have been previously proposed. And it's doing that without any sulfuric acid hydrate as well. And I'm not trying to say that this means there's no sulfuric acid hydrate on Europa, but it is an illustration that the behavior of a natural assemblage like this is maybe not fully predicted from just the behavior of single pure phase salts measured in the lab. Just to mention that we think at Stolz we have hydrohalite here, which makes sense because there's a very chloride-rich deposit. And these features, like Jennifer was saying yesterday, are typical of dihydrate salts like the gypsum. And we're not seeing really any of these features at Lost Hammer, even though Lost Hammer contains up to 28% chlorides. So that's telling us that maybe sulfates are able to sort of spectrally obscure things like the chlorides in these natural assemblages. So one of these proposed models of sulfates being formed through exogenous processing, we think maybe we have two N-member analogs here. Stolz, a very chloride-rich deposit, forming a kind of analog for a very young, pristine deposit on the surface of Europa. And as it's processed by exogenous sulfur delivery, becoming more and more Lost Hammer-like down here. And obviously, if the ocean does contain sulfates, and we are depositing sulfates from the interior onto the surface, then it's possible that the Lost Hammer could form an analog for a more young, pristine deposit. So this is kind of the last slide before I move into the conclusions. We can take our 100 Kelvin data and resample it to various instrument band passes. So the red line here, so this is the same set of springs, Color Peak, Stolz, and Lost Hammer. The red lines here are NIMS resolution, and then we have MAGIS, which is the instrument on the JUICE spacecraft here. And obviously one of the first things to notice is that these spectral details from the gypsum and from the chloride salts still just about visible at NIMS resolution, and we don't see them at Europa. But what's really striking is that Lost Hammer, especially if we ignore this very steep albedo slope into the visible and just look at the continuum removed major water absorption bands, are really closely approximating the Europan band depth, band width, and also at NIMS resolution, you're really sitting on top of some of these band minima measured by NIMS. So it's really these future instruments that are going to be able to tell us whether the Europan deposits are more or less Lost Hammer-like than they currently appear. Right, so now establishing an analog like this allows us to do a lot of detailed work, understanding it in its natural environment. We can look at microbiology, how microorganisms might survive, make a living, and also become entrained and leave signatures in the salt deposits themselves. That's something that we are ongoing work looking at that. We can look at long-term dynamics of deposits like this and how they evolve over time. We can look at how geochemical processes in the subsurface might also become entrained and evidenced in the salts up here, and what we can learn about what's going on in the subsurface. Oh, and also something I didn't put on the slide, but has been mentioned time and time again this week, is radiation. We can use samples of natural salts like this to look at radiative processing of natural assemblages. So, just to summarize, hopefully given you some sense of the value of natural analogs. Salts on Axel Heiberg, they provide sort of a natural complement to lab measurements, hopefully some kind of synergy there, showing that maybe the behavior of lab salts is not fully predicted, natural salts not fully predicted by experiment. Different springs in Axel Heiberg could represent different sort of end-member scenarios for deposits on Europa, and really importantly, we could locally at least form very sulfate-rich deposits from a chloride-rich ocean, even if it just has a small amount of sulfate in it. Yeah, so that's basically it. Just want to thank a lot of people who are helping work on all the detailed stuff that I'm doing, and I'll take any questions. Sorry if I ran over.
It's a really interesting and fun talk you gave. Thank you. I got a couple questions. Can you explain again why these salts are sulfate rich, even though the water is chlorine dominated? And then also for the Lost Hammer Dome interior, why do you think it is the features aren't there at cold temperature? Well, what is it somewhat amorphous? Have you looked at the reason why some of these spectral features aren't present?
For the first bit, it's probably a transport issue. So you're hitting, once this brine comes to the surface, this is Lost Hammer again, but I might go back to this picture. So that's the outlet there and the dome, and then you have the outlet channel flowing downstream. What's probably happening is that once you get to the surface, you're hitting saturation for mirabolite very quickly at these temperatures. The sub-zero temp C, you're precipitating mirabolite very quickly in this region, and then as you flow downstream, the chlorides start becoming more and more dominant further downstream, which are just evaporatively concentrating. So that's just basically saying that locally you could have transport mechanisms which give you compositional changes.
Got it. Thank you.
In terms of the vent interior stuff, so we don't really know. One thing that's really hard to, these salts are quite hard to handle. They change, they recrystallize, they get wet, they dehydrate. You know, they're very hard to actually keep stable and analyze as they were in the natural environment. It'd be great to go back and do some in situ measurements to really look at how things are looking, you know, in the natural environment. It could be a whole combination of things going on here. You might have some amorphous phases in there. You might even have some water ice at these temperatures, things that are dehydrated and then frozen out. But it's a complex assemblage that we don't fully understand. It's a bit of a black box, actually. But we're trying to look into it.
I'll just say that some of the modeling and other work that I've done with the salts supports that theory that, you know, basically your sulfates are hitting saturation a lot earlier. The solubility limits for sulfates are nowhere near what they are for chlorides. And so...
Especially at those temperatures.
Especially at those temperatures, so they're going to precipitate out first. And so you'll actually maybe see more of the solid sulfate, even if you have a chloride or chlorine-rich liquid remaining.
Yeah, exactly.
So somebody else had a question.
There was one at the back.
That was an excellent talk. Where are some areas that you feel like this might fail as an analog for Europa, for the surface of Europa?
Well, an obvious one is temperature. So in the natural environment, we're getting low temperature for Earth, but it gets nowhere near temperature for Europa. Another one is obviously pressure. We have a heavy atmosphere here, which we don't have there. And then potentially another one is ice to salt ratio. I'd really like to go back in winter. I mean, you can't really access this thing in midwinter, but you can get up there in sort of April time, which is still Arctic winter, and look at, you know, these things get iced, and you have ice and salt mixtures precipitating out, things like that. So I think that would be a really valuable thing to do from that standpoint.
In terms of the temperature and pressure, do you think that these will shift in a predictable way? I mean, is it something that you could scale?
This is, well, with the temperature, we've done some of these measurements to factor this in exactly, but I think that this is an argument for that integrated lab and field approach. We can actually use the natural samples which have formed and precipitated from natural fluids and then take them into the lab and do the same kind of experiments that we've been doing with the pure phase salts, you know, for a while, and compare those two results.
Brianna? Yeah, picking up on that last point, I mean, I absolutely love this idea that you've got these intimate mixtures. You've got natural sorts that you can actually take and do the lab sorts, so you can get away from that whole linear mixing and the thing that Brianna was talking about earlier on of what interactions you get. In terms of the provenance, though, I don't, maybe I'm missing something, I don't get why this isn't a better analog for Mars. If you've got transient water and very high salt concentrations, that seems like the inverse of what, I don't understand what the processes would be, where the dominant cycle we've been talking about for the last couple of days is probably mostly about the exogenic sulfur delivery and what happens to that.
Yeah, I think.
So for the geologic setting, it seems these small. I mean,
Yeah,
you've got small amounts of meteoric water that come through in pulses and redistribute the salt.
Yes.
And we don't have like continental lithologies that have given rise to the evaporites to start with. So
Sure. I think as a full sort of geologic process, you're right. That's not where the value as an analog actually comes from. I think it's important to know, when you're doing analog work, there's certain aspects of it that are high fidelity and then others that aren't. And I think in this, what the real benefits are looking at actually the salt precipitation from the brine, how that functions in these kind of assemblages, and then what that means for the remote detection stuff. I think that's really where the value is here. And you're right, I mean, you could absolutely use this as analogous to other processes on other planetary bodies as well. I don't think it's an either or.
Maybe the last one is Brianna here.
So are there plans to go back? Are there plans to use different instruments to
I would love to go back. I would love to go back and do some in situ stuff. I would love to leave some data loggers in these deposits to look at sort of hydration state changes and things over time. It's not cheap. So I have plans, but I have no funding to do it right now. But that's kind of the goal, is to go back, yeah.